let's talk about reference angles. Reference angles are going to be very useful throughout the course because they allow us to take an angle that's in the first quadrant to see how it behaves in the second, third, fourth quadrant, or conversely take something that's in the second, third, fourth quadrant and think about a more simple angle, something that would just be in the first quadrant, a positive acute angle. And that's kind of the key to these things. A reference angle is a positive acute angle formed by the terminal side and the x-axis. A lot of times I'll say the nearest x-axis. So if we think about a given angle theta, we're going to use the following formulas to find the reference angle, and the reference angle we indicate with this theta prime. Notice I haven't actually given us any of these formulas because any of these equations, we're going to create these as we go. And so let's just start with an example. I'm going to start with an angle of 23 degrees. So the first thing that's very important whenever we're finding a reference angle is to think about the position of this angle. And I'm going to sketch it too, because I think a sketch helps not only in terms of determining the quadrant, but it's going to help me determine those formulas. It's going to make those formulas a lot easier. So I know 23 degrees between 0 and 90, that would be sitting in the first quadrant, somewhere around there. That's just kind of a ballpark. So we want to find a positive acute angle. Right now we have this angle in black, that's our angle theta. We want to find a positive acute angle formed by the terminal side and the x-axis. Remember I said we can think of this as the closest x-axis. Well, clearly closest to this side is our positive x-axis, meaning this angle right here has to be the reference angle. So the reference angle is one and the same with the initial angle, and that's going to be our formula for quadrant 1. Theta is just equal to, or I should say our theta prime, our reference angle, is just equal to theta. Very easy in the first quadrant because all angles in the first quadrant are already positive and acute. Now I should note that if we had an angle, say, of 383, this is a coterminal angle to the 23 degrees. It's a full rotation, full 360, plus 23 more. Well, that would be, the reference angle there would be 23 degrees. So when we say that these reference angles are equal to the initial angles, it does have to be less than a single rotation. It has to start as a positive. So if we saw something like the 383, the first thing I would do is say, hey, I need that to be within a single rotation. I'm going to subtract 360, and then we get that reference angle right away. So we do want to make sure that we are starting with an angle that is between 0 and 360 when we use these formulas. Otherwise, we have to apply our ideas of coterminal angles. Let's take another example. So this time I'm going to take an angle that's a little bit larger. Let's set our initial angle to be 145 degrees. So if I think about 145 degrees, I know that that is between 90 and 180, which places it into the second quadrant. 145 is 55 degrees off 90, it's 35 off of 180, so it's a little bit closer to the x-axis. But again, just kind of getting a ballpark of where that angle would be, this would be the angle taking us into the second quadrant. But I want to know the angle between the terminal side and the closest x-axis, so I'd be looking for this blue piece right in here. So this time I have a little bit of math to do. I have a calculation I have to do. I want to know this blue piece. So if we look at what else we know around this little blue piece, I know to get from where we started to this negative x-axis, that green angle would be 180 degrees. We just traveled around theta units, or 145 degrees. So to find that remaining blue portion, I just need to subtract these two known portions. So I can find my reference angle by taking 180 and subtracting 145 degrees, and that would leave me 35 degrees, and that should sound familiar because I said that's how far off we were from the x-axis at the very beginning. So anytime I have an angle in the second quadrant, because we're coming up short of that negative x-axis, and we know every single time the negative x-axis is at 180 degrees, we're going to take that 180 and we're going to subtract off whatever the initial angle was. Let's take another example. Let's say this time we have an angle that is 220 degrees. So theta is equal to 220. Well, 220 I know that this is 180, 220, a little bit further, but it's not bigger than 270. So that angle is going to be act a little bit closer to the x-axis than it is to the y-axis. We know it's 40 degrees off of the x-axis, it's 50 degrees off the y-axis because it's 40 degrees off 180, it's 50 off of the 270. But we want to know the reference angle. Right now we know this angle, but I want to know the closest x-axis. I want to know that angle right there in blue. And they are always positive, so I'm putting an arrow on it, but really I don't care about the direction. I just want it to be a positive. I don't care how I have to move to get back to the x-axis. I want to know that distance in there in blue. Well, just like we said before, we know the distance from positive to negative x-axis. The black is also known, that is the angle that is given. So to find that blue, I'm going to have to do a little subtraction again. But this time, to find my reference angle, I'm going to take my initial angle, the 220, and subtract off the x-axis, or the 180. And that leaves me an angle of 40 degrees. Squeeze that in. So 40 degrees, and we do want to make sure we always have our degree symbol sitting on these things, otherwise we would have to read those as radians. So anytime we're in that third quadrant and we want to figure out the reference angle, anytime we're in the third quadrant, we've overshot the negative x-axis, which means we're going to take our angle, our initial angle, and subtract off 180 degrees. We have one more formula to determine, and that is if we have an angle in the fourth quadrant. So let me set an angle of 283 degrees. Well, 283 is just past 270, but it's coming up short of 360, so we do know that this one is in the fourth quadrant, just a little past the y-axis. In fact, we know it's 13 degrees past the y-axis. I do want to know how much further it is to get up to the x-axis. I always want to know to the x-axis. And so if I think about how to find that reference angle, we know the distance the whole way around. That is a full rotation, or 2 pi. I'm coming up just short of that. How much short of that? Well, let me subtract off the known amount that we went around. So to find my reference angle, theta prime, I'm going to take my 360, full rotation. I'm going to subtract off the known angle of 283. And when I do that, I get 77 degrees. And so if we want to write our formula for that, if we're in the fourth quadrant, theta prime would be equal to 360 minus theta. So notice every single time we're using either the initial angle itself or we're using 180 or 360 in some way. I never use 90 and I never use 270, even though at times it might seem like, hey, it's easier just to count off 270. 270 is only 13 degrees away. Well, yeah, but we never want to measure from the y-axis because that's just not the definition of a reference angle. Reference angles always measure off of the x-axis. So we're always going to use either 180 or 360. And again, these formulas only work when our angle is between 0 and 360. However, there's another very important or very common way our angle is written, and that is in terms of radians. And so if these formulas are all true when we have degrees, but what if I have a radian measure? Well, all we're going to do is we're going to change those degree measurements to their radian equivalents. So in the first case, it's not going to change at all because we didn't ever put a degree symbol in there. So radians equals radians, the reference angle equals the initial angle. If our angle is in the second quadrant, to find our reference angle, we are going to take pi and subtract the angle. If our initial angle is in the third quadrant, we're going to take our initial angle and subtract pi. And then in the fourth quadrant, we're going to take 360's equivalent, which is 2 pi, and subtract theta. I'm not going to do any examples in this video, but I will note that we can go backwards and forward. So if we start at a reference angle, we can also take that and we can develop the initial angle from there. But let me practice with these a little bit more. Let me practice with these radian calculations. So let's do a few examples. So let's take an angle of 4 pi over 7. And even though now I have formulas, I'm going to completely ignore those. I'm just going to draw my picture, and I'm going to think about where this thing is. So 4 pi over 7. Well, I know that this is pi, and 4 over 7 is definitely less than 1. So it's in either the first or the second. 4 over 7, a few different ways I could do this. I could get a common denominator between pi over 2 and the 4 pi over 7, which would be 14, and I could compare where those sit. Or I could think about, if this is a whole and this is half of that, well, half of 7 would be 3.5, meaning 4 is just past that. So I'm looking for this angle right here, the closest x-axis. If I want my reference angle theta prime, I can see that I'm almost going all the way around to pi, but I've come up short of that. So how much short did we come up? I'm going to take the pi, subtract off 4 pi over 7, and my common denominator, of course, would be 7. 7 pi over 7 minus 4 pi over 7 would be 3 pi over 7. Let's take another example. Let's say we have an angle this time of negative 13 pi over 9. Now we have a few options here. We can't use those formulas as it currently stands because this is a negative angle. We said those only work with angles that are positive in between 0 and 360 or 0 and 2 pi, single rotation. So I could sketch this thing out and just think about it. Negative 13 over 9 I know is greater than 1 less than 2, so it's in either the second or the first quadrant. We're traveling backwards, remember. And then half of 9 would be 4.5, so this is 9 pi over 9, and this is 18 pi over 9. Well, this would be 13.5 pi over 9, so it is going to end up in that second quadrant. However, we might be less comfortable working with the negative angle, so we might just want to be able to apply those formulas directly. So what I can do is I can find a coterminal angle. We should remember how to find a coterminal angle from before. We get those by adding, subtracting 360, or in this case, we're going to add 2 pi. And so if we add 2 pi to that, we get 5 pi over 9. And so we can see that that is in fact in that second quadrant, because 5 over 9 is just over the 4.5 that we would have here, so just a little bit beyond that. It is half pi over 9, or pi over 18 away from the y-axis. I don't care about that at all, though. I want to know this distance right here. So to find that, we're going to do the same thing we actually did in the last case, which is to take the pi and subtract the 5 pi over 9. And when we do that, 9 pi over 9 minus 5 pi over 9 is 4 pi over 9. Now I could have used a negative 13 pi over 9 rather, and I would have had to remember this is negative 9. I'm going 4 more past that. So just simply by counting, we can see that we get that 13 pi over 9. Let's do one more. Let's take 29 pi over 4. Well, here there's a lot of rotations here. I have no idea where this thing is sitting, so I'm going to subtract some of those rotations. Again, I'm finding a coterminal angle first in order to find my reference angle. So it is important to note that coterminal reference angles not the same. So coterminal angles, I'm going to subtract 2 pi. So if I subtract 2 pi, that's the same as 8 pi over 4. Subtract it once, I get 21 pi over 4. Of course, I'm going to have to subtract this a few times, so I could have done it more efficiently. I could have divided 8 into 29. Would have gotten 3 whole times, leaving me a remainder of 5. But if we keep subtracting the 2 pi, we'll get there eventually too. 21 minus 8 would be 13 pi over 4, and then subtracting one more full rotation, we get that 5 pi over 4. I said just a second ago we should expect. Again, we can divide by a full 2 pi, or 8 pi over 4 rather. Divide 29 by 8, we would get 3 full rotations with 5 as a remainder. So all of these would be coterminal angles. Let me put them in boxes. Not what I'm after. But they do get me closer to my answer, because now I can see what that looks like on my axes. 5 over 4 is just past a hole, but it's not not up to 3 over 2 yet, so that would be where my angle is. I want to know the reference angle, meaning I need to know that angle right there in blue. So we have an angle that's greater than the negative x-axis, the pi. So I'm going to subtract off that pi. I'm going to take the 5 pi over 4 and subtract by pi. Scroll down a little bit. And so when I subtract those, I get pi over 4. And so that would be my reference angle. Let me call it theta prime. So even though we do have these formulas to assist us determining what the reference angle is based on the degree or the radian measure, it is a lot of times easier, I think, if we really understand what the definition of these things is, just to draw it out and to think about how much further do I need to go or how much did I come up short of reaching an x-axis.